grade distribution versus distribution of measurements. Okay. So, so anyway, so if I give you a test, okay, so we have score, okay, and let's say aptitude. Okay, so we can, if we want, graph the point distribution, or we can graph the cumulative distribution. So let's say that I have aptitude, and let's say I've set things so that this aptitude is about 3.5 level, and let's say that might roughly correspond to an 80 on my exam. Okay. So one possibility is that I could have a bell curve of results. So it might look like this. Okay. Another possibility is that the grade distribution actually, so this is, I'm sorry, score. Yes, I mean, so this, sorry, what I really mean is number with a given score. Okay, so I can model the frequency like that. I might have this. So this would tell me also distribution of grades. I might have a class where the distribution is like that, where most of the students ace the exam. I might have, maybe the exam was very tough. I could also something like that. But that's not actually what we're going to talk about. Instead, what we're going to talk about, so this aptitude theta varies in population. Instead, what we're going to look at is a histogram of scores of multiple measurements of trials from population of equal theta, or rating. Okay? So as I said, the grade distribution can vary, depending on the class, the composition of the population, but this is different. We're assuming that we have a uniform population, everyone of exactly the same ability, and we're giving the same person tests. Now, this is assuming also equal composition of tests. Okay? So for such a person, so for such a case, we're assuming more or less that maybe we have a bank of 10,000 questions for a course. And to compose 100-question exams, we randomly draw 100 questions from this bank, so that we can assume that the tests are usually fairly close to each other, fairly uniform in composition. We might separately have judged that all of these questions that are on the exam are a similar difficulty. Okay, so we're going to assume equal composition of the tests. When I switch to chess, we're going to be talking about players of a given rating, and we're going to be agnostic about the composition of the games. We're going to assume the games are more or less following the same distribution, though you will shortly see cases where that's violated. That's going to be our working assumption for the moment. Okay, and you'll see how my model is going to compensate for the factor of the non-uniformity of the nature of the games that people play at different times in different tournaments. Well, let's assume this is uniform. So anyway, so now let's just say that theta is 3.5, and 3.5 is sort of B plus A minus, and on my grading scale, that's my usual curve, that's an 80. So this is the expectation. Okay, so X marks the spot. That's the mean. That's the expected score. Okay. Well, this is a situation where the central limit theorem applies. Implies that what you're going to get must be a bell curve. Okay, so this now is your probability. So in green, instead of number with a given score, this is your probability or frequency of registering a given score. Okay, so by the central limit theorem, regardless of the distribution of the answers of the exam, multiple trials, so as the number of n of questions increases, this becomes a bell curve. Okay. So that's regardless of the natural distribution of getting answers to questions. So there actually, by the way, there are two dimensions of trials here. One is the number of test questions on the exam. So in some sense, your score on an exam is already the mean of the distribution. And the second is that we can do multiple measurements. We can give multiple exams, giving multiple exams to multiple people in the population. Okay. So now, this, by the way, happens also regardless of independence in the original distribution, because the multiple trials are building their own independence on the distribution. Now, this is where we have to be a little more critical of our assumptions. So, for instance, if I'm giving that humorous sample exam that I gave, there are three dimensions of independence that we could consider. And I'll start with the highest one. Suppose I did that every year in this seminar, and every year this seminar was taken by 30 mostly master students. So similar population, and so we'll assume similar ability. And those students hopefully don't communicate with each other about the exam. So then I'm entitled to assume morally that all of those offerings are independent. Okay. So that's independence number one. Okay. Now, within an offering of the exam, there were 30 of you, and you all come from various different backgrounds, most of you from India, but I factor that in. Insofar as you're different people and not communicating on the exam, I'm entitled to assume that your answers are independent. That might not be completely true. There may be cultural factors involved. So, for instance, the question about China would more likely be gotten correct by a Chinese person. But adjusting for factors like that, one could assume that results between people on an exam are more or less independent. Now there's the third and most controversial matter, and here independence is equally false in my chess model as it is in exams. But we're going to be entitled to make a little bit of fudge about that, and that is independence between questions. Okay. Now on the face of it, independence between questions, even on my humorous sample exam, was false in some places. Maybe it was true for the first 4 questions, because they were scattershot, they were all over the place. if I had asked 4 questions about linguistic origins of words, or 4 questions about countries of the world, or 4 questions about colors, then maybe that wouldn't have been so independent. However, the 3 questions that I asked about cricket, they very clearly were dependent. And maybe I probably should have regarded them and graded them as one big question with its own weight. Okay, so one factor that's going to be in the background, and that you'll see is in the background of my chess code when I show it, is that I can assign weights to the various moves, and the weights could more or less be the number of points at stake. So maybe, so each question as it stood was, what was it, worth 10 points or 5? I forget what I said. Worth 5 points. Each question as it stood was worth 5 points, but maybe the 3 questions together, cricket questions together, would have been 15 points, or given a weight of 3 instead of a weight of 1. Okay, so by jiggering at the weighting, you can play around a little bit with independence. But the other thing one can say about an exam, though, is that it is mostly independent, at least a hodgepodge exam like that. Okay. If the exam were all about, oh yeah, well certainly my 2 questions about C++ code were not independent of each other, but kind of what the second question was getting at was a level of depth that was really on a different plane. It was independent of the basic assumption that you know how to count a loop, which is what the first question was aiming for. So there was some independence between those 2 questions in terms of what was really being tested for, although someone who has no idea about C++, if that person did not get the first question, probably automatically was not going to get the second question. So there was dependence there as well. But the point I'm making is that that dependence on this exam was fairly isolated. Okay, 3 cricket questions here, 2 C++ questions there, but between those questions and the others, in what's called the covariance matrix, which in this case would be a 10 by 10 matrix, most of the pairs of entries, you would say, were fairly independent. Now, on an exam for a course, depending on how specific the course is, that might or might not be true. In an intro or survey course, you might find that different sections of the course are pretty independent of each other. So then a final exam would also have a fair degree of independence of the questions. Now, what happens in chess? Okay, so in chess, it is not true at all that move decisions are independent. And I'm going to show the stock example that I use of failure of independence in positions at chess. So let me find this. Okay, so this is possibly the most famous double blunder, okay, in the entire history of chess. So let's watch, first of all, this is between the current world champion Magnus Carlsen and the previous world champion Viswanathan Anand. And what I'm going to show you is an explanation for his double blunder. So this was the position. Okay. So what happened is that White's king had been there. White put the king on d2, which is really putting the king in the lion's mouth. Let me make this a little bigger, or a little bigger. Okay. So Carlsen was really putting his king in the lion's mouth. And what Anand could have done was Anand could have taken this pawn. Now, ordinarily, that's putting the knight in take to White's rook here. But it's also uncovering an attack on White's rook here. So actually, after the knight takes this pawn, White would have to address the attacker first. And in the normal course of things, and as was the case on the previous move, Black would need to recapture the rook, and then White would be free to eat the knight. And White would be a knight ahead. Black's a little lashing out would have done nothing. But because white placed the king here, after the knight takes the pawn and Carlsen takes the rook, the knight can first give check to the king on what is now a safe square. And if white's king moves up to attack the knight, black has another square from the knight from which it can't be assailed at all, giving check to white's king, and then black will be free to capture the rook. Okay. So, however, Anand did not see that. Instead, what Anand did was he had just previously moved this pawn, and he moved that pawn again. He had a fixation on that pawn. So let me show the video. And from the video, just from the manner of the players, you can see what's going on in Anand's mind. The video is on here. Oh, no, I'm sorry. Video is here. Okay. So I'm going to play the video of this. Okay. So Carlsen has just moved his king. Anand had just moved his pawn. Anand's thinking. He's thinking. And what he's doing, you can't quite see it on the video. What Anand is doing is he's looking at that pawn. He had just moved the pawn on the previous move. He can win the game by capturing Carlsen's piece. Let's get the lights down a little bit, by the way. The lights down halfway. So the point I'm making is that my model, if I assumed that moves, like test questions, were independent, then I would think that Anand had a fresh chance of seeing the knight, but instead he moved the pawn. He moved the pawn again 2 moves later. Okay, so completely missing his opportunity. And Carlsen has just face planted his head, because in the meantime, Carlsen had seen the mistake he had made, and then was trying to keep a poker face, and then with relief realized that Anand had not punished him. Okay, so this is a counterexample to my model's basic assumption that chess moves are independent. Okay, it's actually the way Carlsen may have seen the mistake right after making the move. Okay, and after Anand missed his opportunity, Carlsen repeatedly lets his head sink into his arms. Okay, so this actually is considered to be the greatest double blunder in the history of chess. So my point is not to ask, gosh, why did these people make such a blunder? My point is to note that the fact that Anand had that pawn at the edge of the board and the necessity of pushing it forward in his mind alters the probability that he would miss his opportunity and make the blunder, because he had a plan in his head. And that plan was executed over a series of 4 moves in that game, which therefore became dependent. However, that plan of 4 moves lasted only 4 moves. So what I believe holds true in chess is that there is a sparse dependence. Okay. So chess moves are not independent, but the dependence is sparse. Okay, so it is a function. So the covariance is roughly going to be 1 over e to the number of move 1 minus the number of move 2. Okay. So this is a very common distribution in physics for instance, the fall off an electric card, or electric field, or a charge, or contact between different points. And so this is an exponentially decaying distribution. So what this is saying and is that the dependence between moves, which is going to be the covariance, the entry in, if the chess game is 40 moves for a player, the 40 by 40 matrix of dependence, the entries are going to be non-zero only near the main diagonal. Obviously, a move is fully correlated with itself, but most of the correlation is going to be only with a move and its neighboring moves. So the covariance matrix itself is going to be what engineers call banded. Okay. So if we look at the covariance matrix, so let's say we have moves 1 to 40. As I said, obviously moves are correlated with itself, so this is going to be full correlation. But then most of the correlation is going to be just in a few cases of adjacent moves. And then off the diagonal, essentially 0. Okay. So if any of you encountered this concept about matrices in an engineering application, a banded matrix? Okay, all right. So I'm just interested in how much this comes off. So this is my model for what the dependence between chess moves is like. And I'll also assume that it's 0 between different games. Okay. Now that also might not be true. Okay. I mean, you took the GREs in 2 or 3 parts on the same day, and maybe after taking the first exam, let's say it was the verbal, you realize you messed up a few questions, and that would put you in an awful frame of mind for the quantitative and make it more likely for you to mess up there as well, and don't forget the analytical. Okay, so it's possible that one can go on tilt. Okay, more similarly, if you're watching the Olympics, if ice skaters have messed up in the early parts of their routines, it's more likely they're going to mess up later because they've just had their rhythm jumbled. Okay. However, that's actually going to be part of the phenomenon that we're going to want to measure, namely, what is the unit of being in form? Is it being up for a game? Is it being up for an event? This will be related to the notion of, do basketball players have a hot hand? If a basketball player is making some shots at one point in the game, does that make it more likely the basketball player will make shots later in the game? Hi. You're welcome to sit in if you like. Yeah, sure. Okay. So anyway, if this picture holds true, so if we have this idea that dependence slacks off, that basically whatever you were thinking at move 23 is pretty much by the boards at move 27, then we can say that we have a picture like this. So this is called sparse dependence. And what I'm going to do is we're going to model as a slight reduction in sample size. Okay? So instead of going through the awfulness of trying to project or estimate a covariance matrix and have that adjust the figures. We're going to do a kind of calculation that's heuristically very well justified, and we're going to assume that this is really, so what we had as 40 moves, maybe we're going to reduce it down to 35 independent decisions. Okay. And that might account. Maybe you play a move and your next move is something you already have in your head. Now, by the way, there is one other factor, and let me come back to this game. Okay, that's different. Oh yeah, so I meant to. Okay, so Carlson and that double blunder. Okay, here we go. So this, all right. So this is now the record of games on. Game 6, this is the one. Okay, so this actually is the record on chessgames.com of the famous double blunder game. So in fact, if I scroll through the game, if I just play a few moves, here Anand moved that pawn, then Anand moved his rook, and he moved his rook back. So this was a repetition of moves, and then Anand went back to that pawn, and then after Carlsen got his king out of take, Anand moved his pawn again. Okay. Anyway, the point is that you might play a move here, and if white takes a knight, you know you've got to take right back. My model is going to deal with that. So you might think that that's not really an independent decision, but my model is going to deal with that by essentially downweighting the significance of an automatic recapture. So we'll allow that my model will adjust for that kind of dependence. But basically what it's going to say is, in terms of the kind of dependence where you're really thinking in a strategy, that maybe the 40 moves played in this game, in this case black played 37 moves, would drop down to 30 or 35 or so. So that's a simplifying assumption that I make, and if you project an exam, you're entitled, as long as the exam is not really all or nothing, okay, as long as the exam is a fair bit of mixing, you're entitled to approach the exam and the distribution of scores with the idea that, that the results on the questions will be independent. But you're going to, what you can do maybe is model the exam as having had a smaller sample size. So if 3 cricket questions are dependent, then you could think of your exam as having had 8 questions rather than 10, or 98 questions instead of 100. Okay, and that's essentially the simplifying assumption that is made in my chess model. Once I do that, and I'm going to do this by adjusting the sample size, and when I adjust the sample size, the place I'm going to reflect it is in the standard deviation, okay, of the bell curve. So now remember from last time that what my model does is, so my model gives each move mi at each turn t a probability p of it. Okay. And we know that for all t, the sum from I equals 1 to L of PIT equals 1. Okay? And L is sort of the number of legal moves. And technically that depends on t, but remember I said we're just going to pad positions with invisible moves that are super bad, that have probability 0, and so we don't have to complicate our notation by making L depend on t, even though it really does. Okay, so that's the situation. So once I've done that, and once I justify my assumption that chess moves are independent, with a little note that when it comes to projection, I'm going to reduce the sample size, okay, to reflect that the variance on my exam was really bigger. Okay, then what I've essentially done is I've reduced chess to rolling dice. Okay, so let's say that my chess model says that the probability of the move A5. Okay, so let's go back. Let's get out of the situation where my model would have been wrong on a given move, but let's just go back to this move where Anand's A5 was actually quite a reasonable move to try to get something going on the queen side. So suppose it said the probability of 23A5, that being the move, equals 0.417 for a player rated 2780, as Anand was. Okay, so suppose my model says that for a player of Anand's rating, there was a 41.7% chance that that pawn would be moved. The process that I'm analyzing is one in which Anand has 1,000-sided dice. One like the gamer's dice that you can see in shops for playing these games where they have dice of 20 sides or so, but this time 1,000 sides. And on 417 sides of that die, I have painted the move A5. Okay. Another reasonable move in this position for black, the position was actually bad. It was hard to come up with a reasonable move. That's part of the reason he moved that pawn. But let's say king c7 would be a reasonable move for black. Really, there's not too many ideas in that position. So 23, king c7. Let's say that was 0.244. Let's say my model projected that. Then we would paint 244 more sides of that die by the move king c7. Okay. And then, well, a lot of other moves for black are really bad. Black actually, see, rook d8, that's not even a possible move for black. Really didn't have very many good moves. So let's say probability, knight takes e5, the move that he should have played at move 26, equals 0.001. Or even less than that, then one side of the die would be done that. And for a really bad move like bishop e4 that no one would ever play, we can say that that's essentially 0, and that move just would not appear. Bishop e4 is simply leaving the bishop and take to 2 of white's pieces. Okay, so that's what my model does. For each chess position, it assigns these probabilities. It paints the sides of a 1,000-sided die because it has 3-place precision. So I really can't scientifically justify having a die with any more faces than that. And then analyzes the game as if it were a process of rolling the dice. And in particular, when it projects how often a player is going to agree with the computer's move, it is using the mathematics based on the rolls of the die, which are assuming that moves are independent. and then it will adjust at the end for the idea that there was really a lower sample size. Let me just say so once you have the idea of a random process and ideas of dependence, let's say now that this curve is doing multiple measurements of students, okay? And let's just say we're looking for factors of difficulty on the exam. So say I have a choice of doing two kinds of questions, okay? And one might be about cricket, and the other might be about figure skating. Okay, so let's say I have a choice. I have a sports statistics type exam, and I'm sort of designing the exam and what's my mood, and suppose I make 10% of the questions, I could say, they could be about cricket or they could be about ice skating. Okay. Or I could mix and match. So the intuition I want you to have is that if I mixed and match, then there would be a little less variance about the mean. Whereas if I give 10% questions on cricket, then that might depend on a major way on whether my audience was up on cricket. Maybe if there was a test match going on, then they would have read more about cricket, or maybe not. And I might expect results in those questions to be correlated, and that could set up a big gap of 10% of scores. So I might have a big error bar here of what the score on the exam was. Same thing, if I gave the questions about figure skating, then how well people did on the exam might depend on whether I gave the exam on the day before the Olympic Games or in the middle of the Olympic Games. Give it in the middle of the Olympic Games, maybe more of you would have looked up figure skating and read about it, some of the history, or realized some things that were refreshed about some things about the scoring system of figure skating. And those factors, again, might move in tandem and treat that block of questions as if it were one block. And the effect would be, if I did that for every block of 10 questions on my exam, then it might be that my exam, the scores would behave as if my exam really had only 10 questions instead of 100. So that would be a case where you can visualize that the major effect of that kind of dependence would be to reduce the sample size of my exam. Okay, and that is the adjustment that I make in the case of my chess results. Okay, so given these assumptions made, then I'm assumed I'm able to use a high school statistics model. And I made these choices for other reasons. I deliberately wanted to keep the science as simple as possible for people to be able to understand. Okay. So therefore the stats are based on the idea of what are called multinomial distributions. And in principle, the mathematics is the same. The ideas are really the same as for the more familiar case of binomial distribution, where you just have flips of the coin. Indeed, for players in the master range, over the run of chess positions that they tend to get into, the probability of agreeing with the computer move is very close to 50%. You see that in my tables. So we can really think of that as a coin flip. Okay, different positions will have different biases, but over a large stretch of positions, we won't go too wrong. And my model adjusts for the differences anyway, of thinking of this as the binomial distribution of coin flips. Okay, so I'm going to flip n coins. How many heads? So the frequency okay, now kind of what's different is I'm putting, in a sense, the score is now on the x-axis. Okay, so now I'm actually really diagramming the frequency of results. I'm assuming the coin does not have an ability. The theta of the coin is 50% head, 50% tail. Okay, so these are modeling what you might call coin flip exam questions. Okay. All right, so the fact that we know is that you have a bell curve. Okay. And the bell curve has a mean, in this case, centered on equals 50%. But I'm actually going to want to think in terms, also in terms of expectation. So here's n. Gain over expectation, so I might call that mu, would be mu equals 0. Okay. So if I put it in units of expectation, then difference from the expected number of heads, then I might score like that with mu. Okay. Then there is the standard deviation. This is sigma. Okay, and this is it's roughly proportional to, sorry, it is actually to n over the square root of 2. So square root of n over 2, I say. Okay. All right, so that's the expected deviation. So if you flip the coin 100 times, then the standard deviation will be 10 over 2, will be 5. And as n goes to infinity, the statistics of the bell curve suggest that a little bit greater than 34% of the results will be between 50 and 50% and in this case 55. I had to give absolute numbers, 55 coin flips. Well, let's ignore the problem of whether 55 should be in or out of the range. Okay, and similarly here, 34% of the time, you get between 45 and 50 heads. Okay, and then there are further. Okay, so we go out to 2 sigma. Okay, so this, by the way, this 34% is all the area under the curve, which I should diagram green. So it's taking all of this area in proportion to the total area under the curve, which is 1, because it's a probability distribution. And then if we take this area over here, okay, this is about 13%. I'll say 13.5%, is a little closer. It's actually 13.6 or 7, something like that. Okay. And then you have the tails of the distributions. This is going out to 2 sigma. Okay. And the ratio of the actual, okay, so the actual result minus the expected result divided by sigma to find something called the z-score. So the z-score is the actual minus the expected divided by the standard deviation. So in particular, what this means is that about 98, okay, so therefore about 97.7% of the time, Z for measurement is less than or equal to 2.00. So that's what the normal distribution. So we measure the actual scores on the exam versus the expected. So it's, in other words, measure your actual number of coin flips. Flipping a coin 100 times. Take the actual number of heads you get, subtract 50, and divide it by 5, and that's the Z-score for your trial of flipping of coins. Okay, so this is saying that about 97.7% of the time, you're going to get no more than 60 heads. Unless you're in the play Rosencrantz and Guildenstern Are Dead, written by Tom Stoppard. If you've ever seen that play or movie, then you realize that the play starts off with 187 or so coin flips, heads in a row. Okay. But nonetheless, in the non-fantasy world, that does not happen. Okay. So, okay, so this is the idea. So this picture is good for a lot of reasoning, and this is exactly what my model computes, but using the actual math of the 1,000-sided die, okay, rather than the assuming everything is literally a coin flip. Okay. The coin flip picture will take you a long way. All right, so now let me show you the current post on the Gödel's Lost Letter blog, which I was helping Dick Lipton post just before class. It's a hodgepodge post, mixing and matching, just mathematical facts. But at the very bottom, it talks about the integral of the function minus a normalization content that defines this curve. So it's e to the minus x squared times a constant that's used to normalize it, but we'll just leave it out. So the real amazing fact that was discovered around 1800 is that this curve is what describes the distribution of results of actual experiments and the frequency of errors that are obtained in scientific measurements when you repeat trials of measuring quantities where you're allowed to assume that the trials that you are doing are independent. Okay. So why should the formula come out this way? Well, we give a little clue. This is talking about a movie, but I give a little, I wrote this in, I gave a little clue at the end that if you multiply both sides, if you square both sides, then you're going to get this left-hand side equal to pi. Well, if you can square the left-hand side by multiplying the integral over x by the integral of another variable called y. Okay. Then when you multiply e to the minus x squared by e to the minus y squared, what you get is minus x squared plus y squared, and that might remind you of the Pythagorean theorem on the circle. And you can use r squared to use x squared plus y squared, convert the integral, and then what you're doing is you're doing integral of shells in polar coordinates. And that's like giving you the volume of a sphere, and then you get an equation that involves pi, and that might make it more reason to believe why you get pi out of it. So there's something very fundamental and Pythagorean about this integral. And it's the amazing fact that this integral is what gives you the Gaussian normal distribution. So in fact, I just realized that Dickerson and I forgot to link. We were supposed to link this to Gaussian integral. Okay. So there we have the Gaussian integral. It's just not multiplied by normalizing constant. You should get 1 instead of square root of pi. But that is handled in various ways. So you can handle it just by choosing a right there to be pi. Okay, so it's actually done differently. Is define the distribution this way. Normal distribution, here are the bell curves for various, so we're assuming that mu is always 0, so we're centering the curve, and then these are the curves you get for various standard deviations, and we can normalize things so that the standard deviation is considered a unit of 1. Okay, and the normalization is essentially exactly what I'm doing in the computation of a z-score. Okay, so this is the normal distribution on a Gaussian curve. Okay, so now let me show you. So basically what my cheating tests compute, or they compute z-scores of results, and then I compare them against likelihoods. Okay, so I'm now going to demonstrate my program in action. I'm going to demonstrate the old version, which has been calibrated, and then we shall come across to using the new version. So in fact, actually, this is the old version of my program, and what I was just now doing is I was using it to measure the intrinsic ELO rating of 5 games played by the famous artist Marcel Duchamp, who will be featured in the next post on the Gödel's Lost Letter blog. Marcel Duchamp was a chess, maybe not quite master, but he was a high-level enough chess player that he participated in the championships of France, finishing 4th in his best tournament, and then was played for the French national team in 5 different chess Olympiads in the 1920s and early 1930s. Okay. But I'm getting that from here that he was not quite master strength, but it has to be allowed that the error bars of my experiment are very high. And of these error bars that you see, the first set of error bars are assuming that there's no adjustment in sample size, that all of Duchamp's decisions were independent. Okay. So that's 2 sigma without, see, the sigma has the square root of n. So if I adjust n down, sigma's going to go up, and that's going to increase the error bars and decrease my z-score. Okay. So if this is with an adjustment of n, and for this measure, I actually adjust n down by a factor of 1.4. Actually, I divide the z-score by a factor of 1.4, not quite the same thing. And you see that these error bars are just enormous. You know, it's a range of 1,700 points. So the real answer I'm getting here is I just don't really know. The real thing is that my exam of Duchamp's games is not enough questions to really get a fix on his chess ability. Okay, but now we're going to look at a few cases where I think I did have, this was only 109 moves surviving from this play in one of the tournaments. Okay. So now I'm going to show a couple of cases. I always lead off with the example of 2 players who were accused of cheating in December 2012. One person was suspected, I should say, I don't think he was publicly accused, of cheating in the London Classic Open. It's the London Classic Open played in London. And the other player was accused in a tournament in Zadar, Croatia. So, so let me first get him. So this is a file of his moves that I have. Okay, and the other player, of whom I have more tests, is named Borislav Ivanov, okay, at the Zadar tournament. All right, so now let me go into my program. It has the wonderful name A.out. Okay, so now the other thing about these players is that they both had published ratings near 2250, but they both gained about 90 to 100 rating points in the tournament. So under the null hypothesis that they played fairly, I have to use their rating after the tournament. So in this case, I'm going to use a rating of 2340 for both players. Actually, 2339 is what I used in the official test. Okay, so let's first load Mr. Guerrero's moves up. Is this text crisp enough to see on the screen? I think so, even for people in the back. Okay. So now I've loaded, and there were 674 total moves, but half of those are by his opponents. So then I go into my code, and my code has various filters. So it's like a very primitive database query. Okay. And one of those filters is I can just take those positions where a given player was on move. So I can type 10, that's the menu item. Okay, so I'm going to call this Guerrero 2M for to move. And then I want to enter his surname, and if his surname is in multiple parts, then I can do a logical add. His surname was Guerrero. Okay, so now I will stop and filter his moves. And I can look and see what I've got. And now I've got 337 moves that were played by the player. By the way, I skip moves 1 to 8 of any game because those are so close to the opening. I don't actually think that those decisions are more a matter of style rather than a matter of judgment of the player's concordance with the computer. In actual fact, I eliminate further moves after that belong to the so-called book of chess, which I'll show you. But let's just do this test without that step. Okay, so now the other thing that I eliminate are moves where one side is clearly winning. I do that for two reasons. One is to cut down on statistical noise in my model, and the second is on the supposition, which has been borne out in a few cases, that a player who is clearly winning would stop cheating, because the person would say, I have this game in hand right now. All right? And I use a threshold of 3 points for that. So I can go in and I can load some preset filters. So EW3, and I could use either menu option 5 or EW3 to select it, is the filter for keeping only those turns that have evaluation within 3. So now I'm down to 270 relevant moves that are the sample for my official test. Okay. And then the last thing I need to do is I need to input the player's rating. So I define, oh, I did the wrong thing. Sorry, I was stupid. I meant to type 12. Okay. All right, so never mind, but I can do this now. Okay. Part 1, EULO rating 2340 is what I said I was going to do. Now, never mind this. So I had to go through a little rigmarole. This has to do with something called percentile fitting. This was my fitting method. Was not include the endpoints. So we have 49 points. Okay, no. Impose distortion fix. No. Cap for delta of 5.00. These are settings that I have to do. Adjust the delta scale. Yes. Okay. I have to do that. And finish it. Okay, never mind. So this is just the basic trial. Okay, now I can do what I meant to do, which is put in the EULO rating 2340. It was already done, so it's overriding a duplicate entry. My model actually builds in a little slack for uncertainty about the rating. So inside it added 26 points to the rating. It adds somewhere between 20 and 27 usually around 25. Okay, so now I'm ready to do a performance test on the trial. Let me just make sure that the trial is, yeah, everything got upended. Right where I did it. So I have to go back to 710. Okay, so now I'll do that. So I can type ahead, and every keystroke is logged. And so now I'm back to my 270 moves. And finally, I'm ready to do a performance test. And I have 4 legacy questions, all of which are answered no. And this is the test result. So up here are the z-scores, and the 3 in this corner are the official ones that I use. And as you can see, the z-scores are all between 0 and 1, which means that his performance was, relative to his expectation, was in this very fat, very normal region of his bell curve. So I return a verdict that this is a clear negative result. If I want to judge the level at which he played, so I can go into my Run Fit menu. Okay. Now this has a laundry list of fitting methods, including the percentile fit, which I used to make the standard, but now, as I will explain, based on the paper that I just gave out as readings, starting Friday, I instead just solve for 2 equations and 2 unknowns for my parameters. So that's my new standard way. I go, and let's call this so this stands for intrinsic performance rating. So now what my model is doing is it's executing a regression, a statistical fitting process that's multi-step that I'll describe. And what it says is that Guerrero's played intrinsically at the level of 24-28. Now, the ELO rating system itself was built with a bell curve in mind. It's been rebased slightly to a logistic curve, and that will be, again, something that we're going to be going through. But it was based on the idea that your strength, your expected ELO rating should match your intrinsic strength at chess. But in any performance where the N is at the level of a typical chess tournament, say 5 to 15 rounds, but in my case converging on 9 rounds, that your standard deviation of performance would be plus or minus 200 points. So the mantra of the ELO rating system, the way it was designed, was that 200 points is 1 sigma. Okay. So remember, Guerrero's rating was 2250. And we'll use ELO's mantra that 200 points is 1 sigma. So then 1 sigma above that would be 2450. I measure 2428. That's within the ELO 1 sigma. So again, consonant with my test performances, that he merely had a good day, but not an out-of-the-world good day. Okay. So I returned these results, and he was duly awarded a prize that had been delayed for a few weeks in the tournament. He won a sectional prize in the tournament. If you look at my own error bars, these error bars are ones of measurement. These error bars come from the statistical regression that I did. So when I'm saying 2428, I'm also admitting that I don't really know. You know, it's within 2 sigma of my measurement. Basically, 2.3% of the time, when I do a measurement like this, I might have boomeranged around and gotten a number lower than his rating. And this is without adjusting my sample size. If I adjust my sample size, my error bars are even wider. So it is a curse, but an inevitable curse of my scientific setup that I can't measure more accurately. These error bars are the uncertainty in my own measurements based on the fact that I'm doing a statistical regression in order to get these results. So the mantra here is when I'm given just a player's games, 270 moves, I'm regressing on small data, and that small data carries a large error bar with it, because I don't really know. And this becomes particularly important when we think of the idea of a player of a given ability, and we're picking 9 of the games the player played at random. We may have just happened to pick games where the player played worse, where the player had an off day. Maybe the player plays badly on Fridays. How do we know? Okay. Anyway, okay, so that's the end of Mr. Guerrero, and let me actually quit the program to clean up some stuff and just restart. Now let's consider Mr. Ivanov. Okay, so 6-5, Ivanov. So now we have 625, a very similar number of his gains from the Zadar tournament. Okay. Let's load the EW3 filter. Now we're down to 557 turns, but we need to create a filter for Ivanov. So we do that, and now we have 276 moves played by Mr. Ivanov. It's almost exactly the same sample size. Then finally, I'll type 12 instead of 1. Okay, 2340. Okay, so I type that in, and again my system builds in Slack. So now we do a performance test of Mr. Ivanov, and this time we get 5 and 6 sigma. Well, this is pre-adjustment, but still. Okay. So his performance, measured in the common units of the z-score, was way out here. Okay. So after I adjust for sample size, at this point my program was not printing the adjustment for sample sizes because I hadn't necessarily fixed it in stone. After adjusting for sample size, I get that this is about a 5.3 sigma deviation. Okay. And there's also a combination rule of these 3 z-scores. So after adjusting for sample size, actually this one comes down to about 5.1 because I divide by 1.